Across the United States, approximately 11 million homes receive their drinking water through lead pipe. You heard me correctly, 11 million homes. You see, my friends and colleagues, lead is a potent neurotoxin. When this pipe corrode, they can leach toxic metal into our water supply. We've already witnessed such devastating consequences in Flint, Michigan, where corrosion control failed. Thousands of people were exposed to high lead levels, and unfortunately, 12 people died. The health, financial, and social consequences were indeed staggering. The proposed solution by the United States Environmental Protection Agency is to replace these lead lines within a decade. One of the best candidates for the job is bimodal polyethylene. BPE pipes are safe, corrosion resistant, and affordable. But before we go installing millions of miles of this pipe underground, we need to answer a critical question. Will they function for a century without becoming brittle and crack? In the molecular level, BPE is made up of long and short chains of carbon and hydrogen atoms. These chains wrap and weave around each other, forming what is known as entanglement. And this entanglement is what gives the pipe its strength and flexibility. Over time, chlorine that is added to disinfect the liquid can scission these chains. When enough chain scissions occur, the material loses its entanglement and becomes brittle and crack. Polymer scientists are seeking to address this problem by adding branches into the network. A branch is like a twig in the network. It locks the entanglement in place. But here is the branch problem. Where should we place the branch? On the long or the short chain? And how many should they be? For if we place them in the right places, we can solve the durability problem. If you place them in the wrong place, it does nothing to that said problem. I want you all to picture this. The fight for the fate of humanity happening in the molecular level between the forces of good, branch, and the forces of evil, chlorine. Here is where I come in. I take the BPE pipes and I subject them to short-term accelerated aging of 4 to 6 months. This simulates decades of operation of this pipe in a chlorinated environment. By combining polymer chemistry and mechanical engineering, I can get the relationship between the molecular structure and the macroscopic properties of this pipe. By linking the molecular structure to real-world performances, we can help pipe manufacturers design better BPE pipes. This would mean fewer replacements, lower costs, and most of all, we can solve the durability problem. This would ensure we provide safe, clean, reliable water for generations to come. This, my friends and colleagues, is the future my research is helping to build. Thank you.